Apologies for the pretentious title. The idea behind this is quite simple. The idea is basically to look at the traditional embedded world that ARM has operated in the past, contrasted with the non-embedded world that we are currently entering, and look at the software ecosystem and how we need to change the way or modify the way we do software for ARM servers. So in the next 20 minutes, we're going to look at the two universes, the embedded and non-embedded universes, and see how they're different. For the purpose of this presentation, I'm assuming embedded essentially means embedded and mobile, and non-embedded would be your laptops, desktops, workstations, and servers. So we'll look at toolchain project schedules, we'll look at distribution schedules, and then we'll try to figure out how we can actually plan CPU support so that when your CPU is shipping, when your server is shipping, your software is already ready for your server. So who am I? I'm Siddhesh. I'm the technical lead for Toolchain in developer services in Linaro. I maintain the GNU C Library, and I commit to GCC and binutils. I have maintained RHEL and Fedora packages in the past for about 6.5 years, and I hack on a variety of FOSS projects. So this is, let's just jump right in. So this is what the embedded universe typically looks like, right? Everything is in one place, and that's the view that you would typically be familiar with. Your user would buy your hardware and would download the toolchain from your website. So as a hardware vendor, you have complete control over the hardware as well as the software ecosystem that your user has access to. Because of that, you can actually time your software releases. You can control access to your software, and basically everything around your hardware, including IP confidentiality. You have a lot of control over it. Upstreaming of the support is secondary when it comes to the embedded universe, because it's not tied in with your shipping. You can do upstreaming once your hardware and your software has been shipped, which makes things very convenient when it comes to timing of your support. The non-embedded universe is slightly different, and it's actually three different universes, so to speak. So as a hardware vendor, you operate in one universe, and then there are two different universes that you actually have to interact with to make sure that your software works on your hardware, right? And I've basically in this chart I've mentioned board, but it's not as simple as just the CPU and the motherboard. You basically need that's short for the entire hardware ecosystem, which would be OEMs, ODMs, and so on. But then that's a separate conversation. We don't really want to deal with that. So if you look at users of non-embedded hardware, they're not going to take software from the hardware vendor. They want software from the distribution, right? And they want software from the distribution because distributions provide support, and distributions make sure that when software breaks, they fix it for you. And distributions, on the other hand, won't talk directly to the hardware vendors and take patches directly from the hardware vendors. What they expect is that hardware vendors talk to upstream toolchain projects, and then they get that software from upstream rather than from the hardware vendors themselves. So this makes a fairly complex kind of supply chain, and it doesn't always work with the IP confidentiality kind of concerns that a lot of hardware vendors have. And because of that, a lot of hardware vendors tend to either delay their support so much so that they might miss their software enablement kind of deadlines, and then you end up in a situation where you have hardware that's ready to ship, but then enterprise distributions don't necessarily have that support, and then you're scrambling to get that support in there somehow. Oh, and the last point, I'm not going to make any comments on that. If you want to fight about it, we can go outside and talk about that. Right, so let's jump right into scheduling, because scheduling is basically where all the logistics kind of comes in. And to actually be able to do anything about it, we need to look at what the scheduling, what the schedules for various toolchain projects look like. So GCC is probably the most complex of the three major toolchain projects. GCC releases annually, right? And it also has various stage freezes. Like in November, you have the stage 1 freeze, after which there can be no major features included. There's a stage 3 freeze that happens in January, after which there are only critical bug fixes that get accepted. And then there's a stage 4 freeze, which is essentially a release. glibc happens twice a year, so it's a little more frequent than GCC, and it's around February and August that the releases happen. There's a development freeze that happens just before, a month before the release, and that gets a little tricky in the February release because the freeze happens in January, and you have Christmas holidays before that, so the freeze implicitly kind of happens towards the end of December, and you essentially end up with a roughly 1.5 month freeze, unless you have a release manager in India who doesn't have Christmas holidays and is working through the Christmas holidays. And then you have binutils, which again has 2 releases a year, one in Jan-Feb and another in July-August. So how can we use that information, right? So for GCC, if you're looking to upstream support for your microarchitecture, your deadline essentially is the stage 3 freeze. So by January, you need to make sure that your patches are posted upstream so that you can have discussions about them. However, a safer target is the November stage 1 freeze, because quite often you'll find yourself iterating on those patches. And that iteration, if it goes too far into the stage 3, beyond the stage 3 freeze, the likelihood of your patches getting in become lower and lower. And the problem with GCC targets are that they're very hard targets, because if you miss that target, your support gets delayed by a year. It's not 6 months, it's not 3 months, it's an entire year that you have to wait for the next GCC to come out, right? So planning for GCC freezes is critical in that sense. glibc is, it's less conservative than GCC, but at the same time, what we found is that there are a lot more optimization opportunities, and there's a lot more scope to do work where you can get a lot of returns for your microarchitecture. So you start early. You need not upstream early, but then you upstream early enough so that it's easier for your patches to be backported. Now the binutils case is a little interesting. Of all the ARM server architectures that I've seen that have had their MCPU flags upstreamed, they've done that in GCC, but they've not done that for binutils. The overriding assumption over there is that there's nothing to be done in binutils, which is almost true, but not quite. And what happens if you don't upstream an MCPU flag for binutils is that if you discover a linker hack that you can do late in the compilation lifecycle, you cannot really add that at the last moment because you don't have a CPU flag. Then you have a GCC flag that was added in 2016, and then you have a binutils flag that was added in 2019, and you cannot really have both of those in the same release cycle. So I would advise in this case is that add the CPU flag. And even if you don't have any linker flags, linker hacks, that's fine. You know, you're just basically hedging against the likelihood that you might discover something that you need to do towards the end of the life cycle.
That's not totally right. The reason we did not add the CPU flag to binutils was because a lot of time in distributions, they move the compiler up, not necessarily the binutils. So what we do is we translate the M CPU option into a bunch of M arch flags. And if you need the linker optimization that you're talking about, you'd probably do that from the compiler driver, and therefore it should be okay. So I'm still not convinced, so I'll probably take that further offline.
Like I said, it's a hedge, right? At this point, yes, you can argue that we'll never need a binutils flag, but then
I'm
if
still
you
not
end
convinced
up,
about the use case.
Sure.
And it was a deliberate design choice in AR64 because of the fact that you had version skew between GCC and binutils. So you wanted to get rid of as many things as you could. So you sort of just said, I'll have the architecture support.
Okay.
And invariably what happens is that the architecture support comes, as far as GNU Toolchain for AR64 is concerned, it comes much before CPUs are announced and so on. So,
okay, but how about microarchitectures? I'm not talking about only architecture support.
So the microarchitectures get announced afterwards. The microarchitectures implement an announced architecture, and therefore the architecture support is in an older binutils compared to when the microarchitecture gets announced. So you have a bit of a thing that you play with.
Right. No, what I mean to ask is for microarchitecture related linker hacks, if you ever need that sort of.
And that can be controlled from the compiler driver is what I'm trying to tell you.
So that's the preferred
Yes.
mode of operations
Yes,
for ARM64.
because most people, if you need the linker hack, you're going to use the compiler driver most of the time.
Fair enough.
And the number of people who directly invoke the linker are probably, you can count them on one hand, if not two, at the risk of, having egg on my face, but yeah.
Okay.
But yeah, that there are mechanisms that will allow you to take care of the thing that the use case that you're suggesting.
All right, thanks. Right, so moving on to distributions. So Fedora, Ubuntu, etc., the fast-moving distributions are not that interesting from a scheduling standpoint because they have a 6-month release cadence. They're not supported for a very long time. So chances are that if you meet your upstream targets, you will meet your Fedora and Ubuntu targets. But then they are still interesting for a different reason. RHEL, Ubuntu, SUSE, I haven't mentioned SUSE because I don't have any experience with SUSE. Hi. So they tend to have a longer release cadence. RHEL 8, for example, is coming out after over 5 years. Before that, RHEL major releases were at 3 years cadence, so that's a very long time. And they end up getting supported for 10 plus years. And they have a very, very conservative backport policy, especially when it comes to toolchains. Because of which it becomes very important to make sure that your upstreaming deadlines are met so that that support kind of lands in the server toolchain. So what do you do in that case? So for Fedora and Ubuntu, like I said, they're interesting, but they're interesting for a different reason. They're interesting for evaluation, meaning that you get software support early upstream, and you're sending your servers out for evaluation to your customers. Fedora, Ubuntu, Debian, etc., Debian SID at least, not the rest of Debian, are very useful to kind of send out to your customers so that they can try out your platform with all of your optimizations early, right, before the hardware is shipped. And for Ubuntu, but there's no such timing limitation with Fedora or Ubuntu. For the long-term support distributions, major releases are literally the only entry point for GCC, but there are some caveats. I'll talk about that later. Update releases may backport glibc optimizations, and this is where things get a little interesting. Where glibc optimizations earlier on in the initial update releases, the 6-month update cycles, roughly 6 months, depending on the distribution. It's easier to do that early on, but in later update releases, it gets harder and harder. And it gets progressively harder until you hit this maintenance checkpoint beyond which they would probably not accept any optimizations. So that's one thing to take into consideration when you're timing your glibc optimizations to upstream. Backports in general are very conservative. New CPU flags and so on and so forth won't get backported, so you need to make sure that your scaffolding, your CPU flags and so on are in early. So here's the caveat to GCC. So the main distribution, the default distribution GCC is one thing, and that usually does not get updated because that's conservative because the entire distribution is built with that version of GCC. And making major changes over there means that you'll be making major changes to the entire distribution. So that's avoided, and that's done only on major releases. As a result, you have something called as a developer toolchain package. I know Red Hat has a developer tool set. I'm pretty sure Ubuntu or SUSE will have their own packages as well, which would package pretty much the latest toolchain that is released and provide like a short-term support, about a couple of years for those toolchains. These are a great target for GCC optimizations. However, even for that, they will typically pick up GCC from the last year, which means you still have like a 6 months to a 1 year kind of latency for that. glibc obviously is not a good target for this because glibc again is a core distribution thing. It does not really belong in a separate developer tool set. So with this kind of information, roughly we can see that if you have a server that you want to ship in 2022, you would probably want to start working on your toolchain strategy now, and try to make sure that your toolchain flags, etc., are there in 2020, which means 2021 you have your when you're actually doing customer evaluations and so on and so forth, the support is there in Fedora, Ubuntu, and it's starting to trickle into the developer toolset packages. And by 2022, when your hardware is shipped, you have enterprise software, which already is able to kind of leverage your platform to the fullest. So that's basically what I have for this presentation. So I'll be happy to take questions.
Not a question, but in addition to that, in particular, when we're talking about adding particular flag, then it is one thing of the vendors adding some new feature flag and that propagating into the distributions as you've outlined here. Another thing is that the availability of the flag will not cause all the distro vendors to automatically actually enable all the flags because it still needs to run on a very common baseline.
Right. Yes.
So having a compiler feature is a very cool thing. If someone wants to compile their own application specifically for one platform, but if it should be available in the distro itself, accelerated or optimized for a particular platform, then that will require to find other solutions in glibc, for example, to adapt to the platform that is actually executing on.
Right, right, agreed. So the flags that I'm talking about specifically are the MCPU flags, which the distribution as such does not need, which is why I said that it's not necessarily a target for the distribution, but the developer toolset would need, because that is what the average consumer, or well, not the average consumer, the high performance consumer for the server platform would need, right? The banks and the financial institutions, where they're basically building their software with for the microarchitecture to try and make sure that they get the most out of that server. So yes, I agree.
No
you don't-
criticism, just adding that for people listening into the
Absolutely,
recording.
yeah. Thanks for making it clear. Any other questions? Going once? Twice? And gone. Thank you very much.